Okay, so we're going to continue on with absorption processes. So absorption. So a lot of the processes that we've talked about, absorption, adsorption, cation exchange capacity, all these things kind of are lumped into this category, and some of them inappropriately, but that's still the way it is. So let's first talk about adsorption. Okay, so these are mainly cation exchange capacity. So this is cation exchange capacity, but also attraction of polar or neutral molecules. So, we can go with polar or neutral molecules into here. So we've got our clay here with our negative charges, and then we've got our generic cation that is outside of it, that is absorbed onto our mineral source. So this is our mineral source here, and this is in our solution over here. And usually there is this little radius right here, this little R radius. The radius of the closest approach determined by the hydration radius of the cation. So there's it can get so close to it, it depends on the hydration radius, which is inversely proportional to the ionic radius. So the energy of attraction is proportional to the charge over the radius. So examples here. So we're going to give some examples here. Say we have lithium, we have sodium, potassium, rubidium, and cesium. Okay, so they're all monovalent cations, so we don't have that indicated here. So this is the lightest of them all, and this is the heaviest. So this one has the small ionic radii, and this one has a large. So this one has a large hydration radii, and this one has a small radiation. So these are weakly attracted to the mineral surfaces, and these are strongly attracted. So these are weak, larger ionic hydration radius, smaller ionic radius, lightest. So we're going to see cesium being more attracted to our clay minerals than our lithium here. And generally our divalent and our trivalent cations are more strongly attracted than monovalent. So generally calcium is much greater than potassium. So, and then trivalent would be even more. So we get more attraction with those things. So keep this in mind so that when you're looking at different things that are inside of the system with absorption, we know that that is the attraction there. However, charge on clay minerals varies. Okay, so there is variation on clay minerals. Not all clay minerals are just, in this example over here, it's just like everything is negatively charged. And that does vary. It varies by the composition. It depends on the pH. And so this is one of the big things that happens with this, is that these things are not all created equal. So the intrinsic charge here equals the intrinsic charge is the net structural charge. Okay, so this right here is the net structural charge. And so this is always negative. And then this right here is the net proton charge. So this is the net proton charge. Due to the loss of OH ions or on edges, this is pH dependent. So this is pH dependent. And this is what we're going to be talking about. So this is pH dependent. So this could be positive or negative. So this one depends on the pH of the system. And so this is really an important part of this, is this idea of the pH. So under normal pHs, it's going to be net negative, but when we hit certain pHs, it changes. So we're going to do our little figure here again. So here we have pH. So we start off at 0 and we go to 14 in here. So this is our intrinsic charge up in here. And we're going to draw a line like this. So this right here, this is our net structural charge, which is always negative. So we're always going to have a little bit that's going to be already there. So like this can't change. So this is the structural charge. And then, so this line here is your Q plus, which is your cation exchange capacity. And then we're going to draw another line down like that. And this line right here is your Q negative, which is your anion exchange capacity. Okay, and then right here, at this point right here, this is called your PZNC. This is the point of zero net charge. Okay, so it's usually around 4 to 5 for most soils. A pH of 4 to 5 in many soils. Okay, so at this point here, it's around pH of 4 or 5. Our cation exchange capacity and our ion exchange capacity both equal 0, and so there's no charge whatsoever. So if we go above this point, which is our normal neutral pHs in our systems, we have cation exchange capacity. If we go less than 0.4, we're going to get anions because we're going to change the charge of our minerals here from being net negative to being net zero or being net positive. So, just to reiterate that, so when the pH greater than the PZNC, you have cation exchange capacity is dominant. If your pH is less than your PZNC, you get anion exchange dominant. Okay, so this is really important to know the pH of the soil. The pH of the fluid that's flowing around inside of it can change it. So when we get to acid mine drainage, all things are weird. Okay, so under normal groundwater pHs, which is usually 6 to 8, those pHs, you're going to see an anion exchange capacity. You're going to see the cation exchange capacity. When we get into lower into there, so the degree of cation exchange capacity here is dependent upon the cation, and so the stuff that we talked about over in here, the radiations, the presence of other cations. Okay, so competition. So if you have sodium and you have calcium and potassium in there, you're going to have competition. The soil and the minerals and their properties. So you actually have to understand the geology of the system and know what minerals are there in order to know what the net negative charge and positive charge that's in there. The pH of the solution. So if the pH is really low, like I said, during acid mine drainage, that can cause it. And speciation and complexation. So what is speciation? Okay. I'm going to pause and change my paper. So speciation, examples of speciation. Okay, so this becomes important here. A dissolved metal, like cadmium, let's use cadmium, can exist in a couple different ways. So we're going to talk about a little bit about cadmium. Because cadmium, there is an MCL for it. I wonder what the MCL is for it. I have to look that up. I will look that up because we should know I don't remember what it is for cadmium. A lot of the heavy metals have, there's MCLs for those. So, but cadmium can exist as a divalent cation. It can CO3. It can relate as cadmium 2, CO3 negative, etc. So it can live as different species and complex. can have different affinity for soils. So depending on the species of the cadmium in there, is it just an anion? Is it a salt that's inside of there? Is it bound to some other mineral that's inside of the thing? It can change it. And the relative proportion of all the different species can change as the chemistry of the groundwater changes, hence the amount of absorption. So as we change our chemistry of our system, we can get into different species going into the system. And so if we wanted to, if we did geochemical modeling, we can do this through and then figure out what is most likely to be in your system. So these things can be depending on pH. It can also depend on EH, or the oxidation reduction potential of the system. So how oxidizing or reducing is the system, and the pH will tell you who's going to be in species inside of there. Hold on one second and I'll show you a geochemical modeling chart that shows this. Hold on. Okay, so you can look these up for everything from uranium to arsenic to anything you want in the system here. And what they are is basically your EH versus your pH. And so you have your pH along this axis, your EH over in here, and then it says, well, if you have a pH of 7 and it's oxidizing, you're going to get Fe2 versus Fe3, or what mineral that you're going to have inside of the system. So this one is for arsenic. So here again, 0 to 14. Here your EH over here in millivolts. This is what we usually mark. So what it usually happens with these diagrams is you get this upper part line here and this lower line right down in here. And these are basically the for natural systems. Now I'm not talking like weird systems like on other planets and really, really super deep. I'm talking normal groundwater systems and normal water. This upper line and this lower line here represent all of the areas that water exists in its normal phase. So above this and below this doesn't exist in our normal natural system. And so this is all the different species of arsenic that can exist depending on the temperature, or depending on the pH and the how reducing the environment is. And then each one of these different species has different mobilities in the environment. So we can talk a lot about these, and we can go into each individual element into the system. So like with arsenic here, depending on if it's aerobic or an anaerobic system or a reducing or oxidizing environment, it will become mobile. So this will become mobile under aerobic conditions, and so you're moving up the ladder here. You're moving up, you can move down, you can unmobilize it. I'm not really going to go too much into this in this particular class because I spent a lot of time in this in my geochemistry class. So I just wanted to get you guys to be thinking a little bit about the geochemistry. So if we were going to talk about speciation, we could go into great detail onto this. So if you guys are looking at any papers for this class or anything like that, you always keep in mind the speciation of the system. The next one is hydrophobic. So hydro, water, phobic, fear, partitioning. This is for organics. So we're going back to organics. This was all stuff dealing with inorganics, with our metals, our speciation, systems like that. But when we have organic compounds, we have polar, so we have nonpolar, or weakly polar, organic molecules. And examples of this is, an example is TCE. Tend to be hydrophobic. That is, they tend to partition from solution into the solid organic matter of the soil. So what will happen is we'll get TCE. It doesn't like to be inside of the water system because they're hydrophobic. They don't like to be in the water. They only have a certain amount of solubility. And so they'll tend to partition into the organic compounds within inside of the soils or within inside of the clays. And so they will tend to stick or absorb onto the soil systems on top of there. And so you can get these molecules sitting into there. So the degree of partitioning really depends on the organic compound. So you have to understand the stuff we talked about at the beginning part of the class in order to understand what's going on here. Organic solids in the soil. So we have a lot of, especially around here, we have a lot of organics in our soil. And since we have a lot of organics, we're going to see a lot of, especially in our upper parts of our soil, absorbing onto those phases into there. So this is really hydrophobic. This hydrophobic partitioning is not dependent like these compounds up here on the pH and the EH. They really are not affected by the ionic strength of the system. It's all deal with solubility. So this process can be important for many, but not all, environmentally significant contaminants. Some weakly polar organics are affected by hydrophobic partitioning, as well as cation exchange and weak bonding and van der Waals forces, and a lot of those other things inside of there. So that is our hydrophobic partitioning, and we already kind of touched upon that, talking about absorption into the system. Number 3 here is diffusion based absorption. So this is really more of like absorption into the smaller grains. So that's the other process that we've talked about. This is that, absorption was, sticking onto the outside. That's these things, the cation exchange capacity. Diffusion is where it goes inside of the clays in there. And the influence of absorption is similar to that of cation exchange and partitioning, except that it's often relatively slow, depending on the grain size in there. And so you can get systems where it diffuses into the soil and then it'll slowly diffuse out with time. And so you could get a lot of that occurring, and this has been one of the main reasons for a lot of very unsuccessful cleanups of sites, is that the system will diffuse into there. And then the last thing is chemsorption. This occurs when a solute is incorporated on the sediment, soil, or rock surface by chemical reaction. So this is a reaction. So there's a chemical reaction that occurs. It precipitates out, something like calcium carbonate. Iron will turn into iron oxide, depending on the system. There's a chemical reaction that occurs, and it can go into there. And so it's really, changing of the system, and we have a chemical reaction that actually occurs. So like CO2 in the atmosphere produces carbonic acid. We can get calcium carbonates forming, especially like I have one site over in Calumet where the pH is 13. And when we have that high pH, we can get calcium carbonate, a reaction occurring right away inside of the system. Okay.